Hello everyone, and thank you for joining my session today. My name is Elizabeth Bishop, and I'm going to do a whistle-stop tour of some of the pitfalls of designing for large-scale AM, which goes beyond simply designing our component for its end-use application. When I say large-scale AM, what am I talking about? We all know what desktop scale AM is, where we've got small build volumes and slow printing speeds. Then got the confusion between large format and large scale. Large format is bigger build volumes, but at the same extrusion rates you would have at desktop scale. We've then got large scale additive manufacturing, which is large build volumes, bigger nozzles, bigger extrusion widths, bigger layer heights, and much faster extrusion speeds. And then we've got very large scale for comparison there. There's a general desire by industry to adopt fused filament fabrication for the production of larger components, but both the production speed and part size are currently limitations. Large-scale systems allow us to print larger things much faster in a shorter time span, but we can also print smaller components faster than we can at desktop, albeit at a lower resolution. And finally, we can also print much stronger components due to the bonding between layers. However, there are several challenges associated with printing at large scale. The first of these we can deem the heat-in problem. Because we want to print much quicker, we need to transfer more energy to the filament quicker. And this often results in printing at higher than usual nozzle temperatures, for example at 250 degrees C for PLA. Conversely, we also have the heat out problem. Because we have a much larger thermal mass, it means that it takes longer to cool and needs to solidify before the next layer can be deposited. The heat in, heat out challenges generally contribute to most of the problems relating to large scale AM, many of which can be avoided through careful tool planning. We also want to avoid failures at large scale because they cost money both in material and wasted time, which links closely to using support material, which not only is a much greater cost associated with the waste material, but supports will also bond to the subsequent layer and need to be removed using post-processing subtractive technologies. And our final issue surrounds retraction, which becomes much more difficult at large scale due to the pressure buildup of the large melt pools in the nozzle. So how do we tackle this? First one is really easy. Avoid the need for using support material through either clever design or orientating the part correctly on the bed. The second one we want to avoid is using self-intersecting infill patterns. For example, the bottom picture there is a self-intersecting pattern which would collide with previously deposited material within the same layer, causing damage to the extruder head. Our second design rule can be to term small feature sizes to be at least 2 times the extrusion width. Without this, you get lots of small singular extrusions with multiple retraction points, which can be difficult to manage. Our next point we want to consider is travel moves. Stringing at large scale is not only a nuisance, but can actually become dangerous with these spiky extrusions that need to be removed with post-processing. Additionally, during travel moves, material in the melt zone can overheat and boil, burn, and become excessively runny due to those elevated temperatures that we can be using. To tackle this, we can create one continuous contour for each layer, incorporating the pattern into the toolpath design. And in addition, we also want to ensure that the toolpath does not reverse direction and print subsequent layers directly over the material that has just been deposited. So thank you for listening. Does anyone have any questions?